In this class, we're going to discuss the Fama-French three-factor replication, and specifically how to replicate the Fama-French three-factor model. First, a quick introduction to the Fama-French three-factor model. The three factors in the model help us understand and compare the performance between stocks of different types of firms. These factors are SMB, HML, and the market, and they are calculated and recorded monthly to show their trends over time. The SMB represents the difference between the average return of small firms and that of big firms. Fama and French found that small firms tend to outperform big firms in the long run, meaning that we expect SMB to be positive. Similarly, the HML factor represents the difference between the average return of value firms and that of growth firms. We also expect this value to be positive, as value firms tend to outperform growth firms in the long run. Finally, market is simply the average return of all stocks in the market portfolio in that month, allowing us to evaluate how significant the S&P and HML values are each month. Now that we understand the factors we need to calculate, we can look at our results to see if they are consistent with our expectations. In Table 1, we show the factor values for the three factors versus Fama-French three factors that you get from Ken French's website. The table shows that 33 months of data were analyzed and all units are in percentages. The distributions of all three factors were almost identical to Fama-French's factors, suggesting a code replicated theirs accurately. In Table 2, we show the correlation between all the factors in our data. We particularly care about the three box values as they demonstrate the correlation between our data and Fama-French's data that is released on Ken French's website. All three factors that we created have close to 100% correlation with the factors that Fama and French created. The slight errors may be caused by different size breakpoints. The slight difference between our market and our SMB and our HML, and their market, their SMB and their HML may be caused by different size breakpoints. While we consider firms with higher than median market caps to be big and others to be small, Fama-French considers them logarithmically, using the 10% quantile instead of the median. However, the differences are minimal as demonstrated by this table. Okay, now we're going to get into the Python code that helps produce these results. First, we create a Google Colab file to code in and connect to Google Drive to Google Colab with the following code. This allows us to import raw data from the Google Drive. Next, we install tools and import libraries. The most important ones are pandas and SQL, which allow us to manipulate CSV files in Python. Not all imported libraries are used, but since they affect performances minimally, the libraries are directly copy and pasted from a template. We also set up two global variables used across the entire project. Con allows us to convert between pandas, data frame, and SQL, and file path is the folder that your raw data is stored in the Google Drive, with each slash representing a new folder. And we get something like this from the output of the code. Next, we import the CRSP data from Google Drive. With the first two lines of code, we read the file in a data frame variable named CRSP 1990 to 2022. And the next two lines print out the data frame and its column names respectively. And we get something like the following from the output of the code. So this is basically what it produces. Next, we clean the CRSP data to make sure all formatting is correct and is filtered properly. So here's where we parse the relevant variables. To clean the data, we first parse the relevant variables to make the data frame smaller and the code run much faster. To do so, we convert the data frame to a SQL with the toSQL function. In this line, CRSP 1990 to 2022 is the name for our SQL. Con is the global variable for converting, which we set up in step 2. And if exists equals replace allows us to replace any SQL file already stored with the same name, meaning we can run this code multiple times without running into errors. Next, we use the variable query to select the relevant variables from the CRSP SQL file. And finally, we convert the SQL back to a data frame with the read SQL function. Next, we convert our variables. The first 10 lines include the two date time and two numeric functions, which convert the corresponding columns into the types date time and float int. The last two lines convert returns from decimal to percentages with a simple multiplication. Next, we create a new filter data frame named CRSP 2018 to 2022. The first line takes dates after 2018, and the second line takes US common base stocks share code either 10 or 11. Then we calculate the market cap for every row, which is the absolute value of the shares outstanding multiplied by the price alternate, and we divide by 1,000 to get the value in millions. In the second line, we replace all zeros in the column with a null value, preparing to drop these rows later. Then we add a column for the exchange type of every row. We first create an empty exchange column, and we use a for loop to go through every index of the data frame, setting the exchange type based on the following rule. If the code is 1 or 31, then it's traded on an NYSE exchange. If the code is 2 or 32, then it's traded on the Amex exchange. If the code is 3 or 33, then it's traded on the NASDAQ exchange. Otherwise, it's an exchange of another type. Finally, we filter out the exchanges of any other types. Next, we add the adjusted return to the data frame based on the delisting code and the delisting return. We again loop through every index and set the adjusted return based on the delisting code. Finally, we drop some columns and then we finish using it to make the data frame more efficient. In the first line, we reset the indices of each row to make the data frame neater. In the second line, we drop the share code, delisting returns, delisting code, and the index column, which was generated after we reset the indices. We set in place to true, so CRSP 2018 to 2022 returns as the new data frame with columns dropped, and we set access to 1, meaning we are dropping columns, not rows. We then print out the new data frame to make sure everything is correct. And this is our expected output of the cleaned CRSP data frame. Now that we have prepared the CRSP data, we move on to the CompuStat data. We import the CCM raw data first in these lines. And this is the expected output of the raw CCM data. Similar to CRSP, we need to clean the CCM data to make it a usable CompuStat data frame. The steps to cleaning the CCM data frame are almost identical to what we did with the CRSP data frame. First, we parse relevant variables with SQL. Next, we convert each column to their correct types. There's a new type for CCM. The apply string function simply turns the column into strings. Next, we filter the columns with the following criteria. Data is taken after 2018. The industry format is INDL. The data format is STD. The link type is LU or LC. And the link is still active during the data date. For the active link filter, we make sure that the link end date is later than the data date. And we also include the case where the link end date is null. This is because we previously coerced the conversion to date time for all link end dates. And that included special cases where the link end date is E, or latest possible end date, meaning the link is active at all times. However, we converted it into a null datetime variable, so we must make sure null link end dates are also included. Next, we add the book value to the data frame. Here we use the coalesce function from SQL, which takes the first non-null value in its parameters. This allows us to go through different columns of null values and floats without complicated if statements. Then we filter for only the last observation of every year for each firm. We do so by sorting the data frame by year and checking if there's a later date in the same year for the same firm. If so, we drop that row. Also note that we have to convert the data date to date time again, since converting a date frame to SQL and back to a date frame causes columns to lose their types. Then we drop the missing infinite values in the date frame and reset its indices. Finally, we add reference dates for every row, which is the June 1st of the next calendar year, and print out the CompuStat date frame. This is the expected output of the cleaned CompuStat data. Next, we construct the stocks data using both the CRSP and CompuStat date frames to generate our three factors. We parse the relevant variables from the CRSP date frame and store it in a new date frame called stocks 2018 to 2022. We also drop the missing / infinite values from the date frame. We've previously added reference dates for the CompuStat date frame. Now we will add it to the stocks date frame to merge the right rows later. Here, the reference date is the previous June 1st. So if the data was taken before June, the reference date is the June 1st of last year. Otherwise, it's the June 1st of the same year. Next, we merge the CompuSet data with the stocks data based on the firm identifier and reference date for each row. When we select asterisks from stocks 2018 to 2022 in line 4, it means we select everything, which includes an extra column of index, so we drop that column in the last line. Then we add the market equity for each row of data based on the last observation of the previous year in December. These market values will be used to evaluate whether firms are big or small for the SMB factor. We first filter for all the data taken in December and set the reference date to the next June 1st. Then we left join the market equity into the stocks 2018 to 2022 date frame based on their firm identifier and reference date again. Then we add the book to market ratio for each row based on the observation on the reference date, June of each year. These ratios will be used to determine whether firms are value, neutral, or growth for the HML factor. This step is almost identical to the previous with just a difference in column name. We filter null slash infinite values out of the data and once again ensure that all data is taken after 2018. This is the expected output of the stocks data. The next step is to sort the firms by size for the SMB. The firm size is the market cap in June reference date, and Fama-French only considered NYSE firms to obtain the median size. We create a size breakpoint data frame with only NYSE firms data in June and parse the three relevant variables: permno, reference date, and market cap. Then we create a temporary group by object named G, which combines all data from the same date into a group. This makes it easy to calculate the median size for any given date. Next, we create the size sorts data frame, which will sort the median size and whether the firm is big or small. For our median size, we first get the group's date, and then we get the group which has the index of that date. And finally, we take the 50th quantile of the market cap of that date. Now we simply sort the firm sizes. If their market cap is greater than the median, it's a big firm. Otherwise, it's a small firm. Finally, we merge the size portfolio column back into the stocks data frame based on reference dated permno. This is our stocks data after adding the size portfolio column. Next, we sort the firms by value for the HML. This process is almost identical to the size sort. Instead of the market caps, we take the book to market ratio to add to our value breakpoints data frame. Next, we calculate the breakpoints. Instead of taking the 50th quantile, we take the 30th and 70th to separate them into three portfolios: value, high, neutral, medium, and growth, low. Here we assign each firm their value portfolios that we just mentioned. Once again, high, medium, and low. This is the final, and we merge the value portfolio column back into the stocks data. This is the final stocks data with value portfolios added. Now that we have the complete stocks data frame, we can begin constructing our factors to obtain our final results. To construct our factors, we first create a group by variable to calculate the average weighted return. In the second line here, we essentially create a list with three indices, and the values of the lists are the weighted average of the corresponding size and value of the value portfolio of the date. This weighted average is achieved by the lambda function, which is applied to the stocks data frame in the same line. For instance, value weighted return returns the weighted average return of small, low book to market ratio growth firms on June 30th, 2020. Next, we create the factors data frame, and we no longer need the firm identifier since there's only one value of data for each factor for each date. So we only select distinct dates from the stocks data frame. Then we add in the three factors for the SMB. We take the difference between the equal weight average of the three weighted average return for small firms, three being high, medium, and low book to market ratio, and the equal weight average of the three weighted average return for big firms. Then we change the indexing of the average weighted returns to make it easy to calculate for the HML. We take the difference between the equal weight average return of the two weighted average returns for value firms and the equal weight average return for growth firms. Finally, we calculate the weighted average returns of the entire market, regardless of the size or value portfolios for the market. Then we filter out the last month, which exhibits a negative 100% return because when we adjusted it, it had missing delisting return data. And we also parse the relevant columns to clean up the data frame. Finally, we ensure the factors data frame are sorted by their dates and display. This is our expected factors data frame output. Next, we import the Fama-French factors to prepare for a comparison of our data versus theirs. We get the Fama-French data from Ken French's website, and Ken French is at Dartmouth. This is what we should get for the raw Fama-French data. Next, we clean the Fama-French data. We first change the column names to match our format. We then convert the three factors to type floats. Next, we convert the date to date time and get the month and year for both factors and the Fama-French factors. This is necessary for left join because while Fama-French's data is taken on the first of every month, our data is taken towards the last couple days of the month. So we must left join by month and year instead of simply by date. Finally, we merge the Fama-French data back into our data with a left join. This is our expected output for the final factors data. From just an eye test, our data looks reasonably close to the Fama-French data. Next, we want to confirm that our data is actually statistically similar to Fama-French's data. We first display the distribution of every factor in our data frame. We achieve this with a simple describe function with the quantiles we want to display. We also run KS tests for our three factors versus Fama-French's factors. The test results can be interpreted as follows. The first number statistic reports the maximum difference between the two distributions, and the second number p-value reports the confidence level of the statistic. For our final step, we show the correlation between all factors in the date frame, and we see that all our factors have almost 100% correlation with their corresponding Fama-French factor. So this concludes the video. I hope you all found this helpful.